Hello, everyone. My name is Samuel Stenerson, and today we'll be delving into an essential concept in the realm of software design patterns, specifically a pattern known as strategy pattern. At its heart, this pattern embodies the principles of flexibility and adaptability in software design. Today's discussion aims to provide a clear understanding of how the strategy pattern can be used in crafting efficient, modular, and maintainable software. The strategy pattern at its core revolves around the idea of encapsulation. Instead of hard coding specific behaviors or algorithms within a class, the pattern suggests defining a set of algorithms, wrapping each one within a strategy object, and making them interchangeable. This enables not just cleaner architecture, but also the power to swap out algorithms at runtime without disturbing the existing system. The strategy pattern is all about flexibility and adaptability. Motivation. Different situations require different reactions or strategies. Hard coding behaviors or algorithms directly into classes can lead to monolithic or hard to maintain classes. The strategy pattern enables decoupling of behaviors, ensuring flexibility and scalability. Understanding the three pillars of the strategy pattern is crucial. First, we have the context. It's akin to the user interface. It's what is interacted with. However, instead of executing algorithms directly, the context refers to a strategy to carry out the job. Then there's the strategy itself, which acts like a blueprint or a contract, defines what methods all strategies must implement. Finally, we have our concrete strategies, which are the real world implementations, and there can be many, each offering a different approach to solving the same problem. So why take the effort to employ the strategy pattern? Well, for starters, it offers immense flexibility. If your application's behavior needs to evolve, it's straightforward to introduce new strategies without affecting existing code. This results in higher maintainability. And importantly, by isolating the algorithmic nuances within individual strategies, we achieve a clear separation of concerns. Each component sticks to its job, leading to a cleaner, more understandable system. Visualizing the pattern. This UML diagram presents a clear view of the strategy pattern structure. At its core, you'll notice the decoupling that was mentioned previously. The context, or main component, doesn't directly bind to any concrete strategy. It operates through the strategy interface, ensuring adaptability and flexibility. Known uses. It's widely used in standard libraries, especially when different algorithms can achieve the same goal because of its simplicity. It's often found in scenarios where a system needs to offer multiple ways to accomplish a task. And this is seen in compression algorithms like zip, rar, or tar, and also in payment processing, such as in e-commerce platforms. A real world use case. Different items, different destinations, and varied customer preferences can all lead to different rates for shipping. So with the strategy pattern, we can have a standard shipping strategy with fixed rates, an express shipping strategy where costs might vary based on weight or speed, or even an in-store pickup where there's no shipping involved. Each strategy is self-contained, and the system can dynamically choose among them based on user preferences or other conditions. And implementing this use case, first, we defined the strategy interface on the top left with just one method to calculate shipping costs with parameters order weight and distance. And then we have the implementations of the three concrete strategies on the right. And first, we had the standard shipping, which in this example, we're just doing the cost would be half the order weight and a tenth of the distance, the sum of that. We also have express shipping, which is 75% of the order weight and 2/10 of the distance, 20% of the distance. The sum of that would be the shipping cost. And then finally, in-store pickup, where we return zero because there's no shipping cost. On the bottom left, we have our context, which uses a strategy. It's a class order with constructor, which takes the parameters order weight, distance, and then also a shipping strategy. And then we just we have our final method to calculate total shipping cost, which is just to return the shipping strategy and then calculating the shipping cost, which is implemented within the concrete strategies. Here we're using the strategy, just showing the example code running. The first line, we have an order of standard shipping with parameters 10, 100. So it'd be weight and distance. And we defined for standard shipping, it's half the order weight and a tenth of the distance. So we should end up with 15 for the first one, and we do. So this is just the implementation of each of our strategies that we defined previously. considerations. I mean, with all design choices, it's essential to strike a balance. While the strategy pattern offers elegance and flexibility, if unchecked, it can lead to a proliferation of classes, potentially confusing future developers that may inherit the code base. Clients or entities leveraging these strategies must have some knowledge about which strategy to invoke and when. On occasions, especially in simpler scenarios, even in the example that was just shown, introducing this pattern might seem like overkill, adding unnecessary layers to the solution. In conclusion, the strategy pattern underscores a core tenet of object-oriented design, which is encapsulation. By abstracting out volatile parts of our application, we're not just making our software flexible, but we're also future-proofing it. It's crucial to weigh the benefits against the complexity it might introduce. In scenarios where algorithms and behaviors frequently evolve, this pattern could be extremely useful. And finally, we just have the references here. And that is it. Thank you all for listening.